Hi, welcome to our Stats. I'm Jacob Cybulski. In this series of videos, I'm going to introduce you to some predictive statistical models, such as naive Bayes and regression, with plenty of data visualization. Welcome back. This is linear regression R, and we're looking at multiple linear regression, and we're going to develop the model properly. In the previous lesson, we looked at stepwise refinement of the model with backward elimination of variables, and I highlighted the need for checking the variable normality, looking for possibly extreme values in the observations, and many other requirements to the construction of linear regression. So let's do it properly this time using exactly the same data set, which comes from the UCI University, and this is the automobile data set. And we're going to predict the price of cars based on the characteristics. And we're going to use only the numeric variable from this data set. I'm going to use three packages here. HMISC, that is used to eliminate missing values, psych for some plotting, and car, which amongst many things, it will be useful in determining the collinearity between variables. We're going to use VIF function, as you can see on the right-hand side. Let's simply deal with all the variables very quickly. Read it, identify the variables, and eliminate missing values which I know existed there. Those specific variables were selected. Quick check with a summary. No NAs listed under any of those variables, which means we don't have any more missing values, which were dealt in a simplistic way by using the mean or the median, depending on the variable type. We could do a better job than that, but that's simple. Let's create a data frame of the candidates for the linear regression model. We use the horsepower, city miles per gallon, peak RPM, curb weight, number of doors, and hope that those variables could predict the price. If we know those 1, 2, 3, 4, 5 variables, maybe we could estimate the price value of a particular car using the data from this data set. Now, those are requirements for the construction of regression model. We have to assume that all variables have normal distribution. We should not have any extreme values. We should avoid multiple collinearity. The variables should have this normal distribution of residuals around the model, and the p-value of coefficients and R2, R squared, and F statistics of the model, we should be always watching so that we get the right formula for the linear equation describing the model. Let's quickly look at the selected variables. We can see that horsepower and price are skewed, and also horsepower, curb weight, they are correlated. City MPG and curb weight are negatively correlated. We'll deal with those issues. The first one is, let's transform the horsepower and the price and hope that by applying log transformation, we'll get a more normal distribution of those two variables. And yep, they look better now, more centrally placed. Just a note that since we transform those variables, if we want to ever refer back to the price or horsepower in the reports, we have to apply a back transformation. Otherwise, we'll be dealing with strange, very small values because the log 10 was applied at this point. So just a reminder, when we do the reports, later on, we need to do the back reverse transformation of those variables. Okay, let's split the data into a training set and validation set. 80% of data will be used for training, 20% for validation. It doesn't matter what the model is going to say at the end, how good it is, how beautiful it is. We're going to test it. We're going to validate that the model performs the way the theory says it does perform. The model, linear model, takes the form of an equation where the price will be a linear combination of the variables, the intercept with the price axis, and several coefficients for each of the variables, which need to be estimated in the process of the model construction. We will be using a stepwise selection of variables by backwards elimination of variables, which means we start with a full set of the candidates, we construct a model, and we'll be dropping the variables one at a time. We will not be relying on an analysis, we will not be analyzing the variable interaction at this stage. Let's see if the model performs well on the whole variables rather than the parts. Also, the model is very, very complex, and a lot of things we're going to do here are unnecessarily complex when we consider the interaction. Here's the first approach to the model construction. The price is a target, and it's a combination of other variables selected from the training sample. Let's look at a summary of this fit, the model, which says that the model now explains 81.5% of all the variation in data around the linear model. So it's pretty good. Usually when we deal with multiple regression, we should be looking at another measure, which is adjusted R-squared, which takes into consideration the number of variables used in the model construction. The basic truth is the more variables you're going to add, the better is going to be the R-squared. So this is a dampening down effect. There's three variables which are already significant. That means they're good candidates for the construction of this equation. It's the intercept, the horsepower, and curb weight. However, as we go through cleaning up of the data, it could be that some of those variables will have to be eliminated. We'll see. First of all, by eliminating horsepower and price by visual inspection, that was pretty good. Now we have a linear model. We could do better than that. We could plot the distribution of errors around the model in those variables and see if the errors themselves have any linearity rather than distribution of the whole variable. That's a big difference. So here it is. It's a very useful plot. It tells us that the fit of the errors around the linear model is in red. The green is the fit of the errors for each of those variables. They are pretty much close, which means that we don't have any very significant nonlinearity in the distribution of residuals around the linear model, okay? Except for the number of doors, which look strange. There is a lot of missing values there. Okay, what are we going to do? First of all, as you can see here in those plots, we have some data which is far away from the model itself. And those data points, observations, they could have some very significant effect on the construction of the model and estimation of those coefficients. So what we're going to do, we're going to look at the measures of distance of those observations from the model. We are going to use Cook's distance measure. And one of the first things to do is to determine the cutoff, at which point we determine the observations to be extreme. Okay, and this is usually involving the number of samples and the number of variables in the system. Okay, so the cutoff is defined, and let's plot. The first plot simply shows all observations used in the training set from 0 to about 170, and it identifies three observations, number 74, 91, and 167, which are extreme. You can see all other observations are close to the model, but we have 3 which are very significant, very extreme. So we're going to eliminate those observations from the training set. And when we do that, the model will be recalculated and it could create new extremes in this process. And here's another plot of the same information, but also it tells us the leverage. That means how important are those observations to the construction of the model and the creation of residuals around the model. So the model at the moment looks like it's pretty much in the middle. It's well behaved, but we can see that observation 74 and 167 had a lot to say as to what the model looks like. And they're extreme. 2 observations here, they must have bent the plane down towards them and upset the equation. And 91 is another one which possibly should be eliminated. Those numbers are actually not raw numbers in the observation set. They are raw names in that data set. So if I want to eliminate them, I will take the training sample and I will identify all of the rows which have the names in the list 74, 91, 167, and I'm going to eliminate them. Okay, it's done. Now, let's refit the model. The model version 2, the summary, you can see that we improved the R-squared value from 81% to 85, nearly 85. You can see that peak RPM variable suddenly gets close to being more significant for the construction of the model. But let's not be so optimistic. Let's try and determine if there's any more new extremes that we potentially have identified. And indeed, you can see that all of the observations which before were hugging the bottom line, they went up, which means that we identify extremes, but they're not as extreme as before. There are some observations, 22, 114, 197, which are far away from the model. And let's see what is the leverage on the construction of the model. You can see 22, 114, 197. Okay, let's eliminate them. They are well within the cutoff area. Now, fit version 3. It's an improvement from 85% to nearly 88% of R squared and 87 of adjusted R squared. Our peak RPM now becomes a good variable to be used in linear regression modeling. Interesting, and the horsepower is slipping back. It used to be very significant and is less and less. Interesting how it happened. Just eliminating extreme values, it completely changes the picture, which means that we need to do it iteratively. We create a new model, we test it, a new model, test it, and let's test it again. The plot. Now we have 3 more extremes, but they are very much within the range of other observations. However, from this plot, we can see that observation 35, it has a huge impact on the model, and so we'll eliminate again. So it's about 3 of them again. And another fit, cutoff, plot. Yep, those 3 variables look not that far away from the rest of the observations. Not variables, they are actually observations. And I think there is the model is quite the fit of the residuals is well behaved centrally around the model. Okay, we'll leave it at this stage. We eliminated about 10 observations from 170 and the model improved tremendously. Now we have 88% R squared. That's pretty good. Now, the next thing we're going to do is to determine if amongst the variables that we used here, are there any multicollinearities? And we're going to use the function VIF, which stands for Variance Inflation Factors. The function which determines which of the variables are mostly correlated with the other variables in the system. And the VIF number will help us identify those bad variables. VIF value, which is above 5, that means that those variables we should be concerned about, city MPG, curb weight, and horsepower, which is well above 5. Above 10 is critical. If you see VIF going into thousands, there's something wrong with the model. Now, which one is causing problems here? We'll pick the worst one. The horsepower has the highest VIF, and so we will delete it from the model. That's a new model without horsepower. And it is expected that when you eliminate it, highly correlated or collinear, multiple collinear variable from the system, your R squared should go down because that variable probably counted twice in the system. We had 3 variables here. Let's quickly check. And now all 3, the remaining variables are well behaved. They don't have an issue, which means that that variable was significantly correlated with curb weight and peak RPM, which sort of makes sense. If you have a heavy vehicle, it should have a lot of power to move. And if it's a lot of power, then most likely rotations per minute is high. Okay, so those variables now look much, much better. However, at the same time, we can see that curb weight and peak RPM, we can trust the coefficients, but number of doors, we cannot. So we no longer have collinearity in the system, but number of doors, that coefficient is probably there's a number we should not be using because the p-value is too high. So let's eliminate it from this set of variables. The R squared did not get any worse. The adjusted R squared, 8749, it went slightly up. And the VIF says that the remaining variables is well behaved. That looks like a good model that we have. We have no more problems with normality, no more problems with multiple collinearity. All of the coefficients can be trusted and intercept. Let's see how the model fares against the validation set. So we're going to use the model to predict the price for the training set and for the validation set. Is a reminder of the R squared for the model. The model explains about nearly 88% of the variation in data. Let's see what is the correlation between predicted price and the actual price for the training set. The root mean square error, and here's the note. If I'm going to rely on the price predicted and actual, remember that they were transformed by log 10. We need to bring it back. We do the reverse transformation of those variables. And mean absolute error, which is the optimistic estimation of error in the units of the price variable. So, which means now it's the correlation between estimated price and the actual price is about 88%. It's actually better than what was predicted from the theoretical prediction. The error in our prediction of the price is about 2,500 and maybe as little as 1,800. which is pretty good, much better than the model we created without doing all those gymnastics in dealing with variables and the correlations and collinearity. Let's see how the model performs on the validation set, the data we've never used for any purposes in the model construction. Um, the correlation is slightly lower, about 74%, and the error in the price estimation is obviously higher, 5,700, and maybe as low as 3,300. Okay, it's still the model performs much better than before, which is great. Now, to do this properly, we should have used cross-validation rather than relying on luck in the division of data into training set and validation set. If we changed one number in this, the seed, which determined the randomness of this whole process of splitting into validation and training, possibly we would have very different results. And the whole process is likely to have been very, very different. We cannot simply replicate the process exactly the same way. Okay, it's every time you have a split in the data, you have to do all of this analytically and analyze it in different ways. So it could be still improved. Maybe we should use other variables. We could use cross-validation to have more realistic estimation of the model performance. Thank you.